In 11.8, we talk about power series. We are going to make the leap from simply, evaluating whether or not a series converges or diverges, which on its own, very, very powerful. Um, but then you might think, well, what's the point? And so we look at an application of series here in 11.8. And this idea is going to continue through the end of the chapter. So as you guys know, your third exam covers up to 11.9. We save 11.10 and 11.11 for the fourth exam, but they do all kind of keep the same theme. We do something a little bit different in the last two sections, so that's a good breaking point. Anyway, in 11.8, it's all about power series. So I put up this introductory example. You can see that document there just above the 11.8 video lectures. So if you haven't seen that one, go ahead and open this up just so you can follow along, since I can't have everything on the screen. If we were in class, I would have this printed for you guys and I'd have it available. And of course, no space to do any work. We'll work on our other paper just to see what a power series is and how this is helpful. Let me go ahead and just read this goal here at the top. We want to find a polynomial function of degree n. We're going to end up calling it p sub n of x, p for polynomial, degree n. We're going to approximate f of x equals e to the x. That'll be a really good function to start us off. Centered at c equals 0. And okay, so how are we going to do this? We're going to go through several steps and eventually we're going to get it down there. We're going to notice the pattern that develops here. Okay, then there's a bonus. Okay. So let's go ahead, and I'm going to assume you guys can see this and the lecture video at the same time. So here we go. Also, while you're at it, pull up Desmos. On your computer as well, so we can see this graph in action. So okay, here we go. Our intro example, step number 1. So it said, let's find a polynomial of degree 0 such that p sub 0 of 0, so that's our polynomial degree 0, equals f of 0. We're going to call that p sub 0 of x. And so you see my steps there to complete number 1. What happened here? So our function is e to the x. We want our function of degree 0 to have the same value as f of 0. Well, f of 0 equals 1. So what is a 0 degree polynomial that at 0 also equals 1? Well, a 0 degree polynomial is just a constant. So for this to work out, we need that to simply equal 1. It's just a horizontal line. So what we're doing is we are making sure that we pass through the same point at 0 that the original function does. The original function goes through y equals 1. So our function goes through y equals 1 at 0 as well. In fact, it's just the horizontal line at 1. Then I've got this note here to compare the graphs of e to the x and our polynomials every time in Desmos. So I'll advise graph e to the x, y equals e to the x, and graph y equals 1, and see, just compare the two. So it's not very impressive after one step. So let's go to step 2. Here we want to find a first degree polynomial, p1 of x, such that p1 of 0 equals f of 0, and p prime 1 of 0 equals f prime 0. So let's take a look here. It'd be probably a lot more interesting if we were in class together, but we're not. So here's what we've got. We want p1 of 0 to equal f of 0. Well, f of 0 equals 1. So we need p1 of 0 to equal 1. The derivative of e to the x, well, it happens to be e to the x. So f prime of 0 also equals 1. So we need p1 prime of 0 to equal 1 as well. So what is a first degree polynomial where both of these things are true? You say, well, first degree polynomial means I have x raised to the first and a constant. So I'm going to write it as 1 plus x. 1 plus x to the first. At 0, I get 1, right? And the derivative at 0 is also 1. So both of these things check out. Okay, so if you've got Desmos up, graph this along with the original function e to the x. And you'll see, hey, now it's got kind of a slope, and it goes through the same y value at 0. And it's still not very impressive, but let's keep going. Step 3, whoa, just caught a breeze there. Step 3 is here. So step 3, and we're going to a degree 2 now, so f of 0 is going to equal 1. F prime 0 needs to equal 1. And the second derivative needs to match. So what is our second derivative of our function? Well, it's the same. So at 0, it's 1 again. So we need all three of these to be true. At 0, it's 1. The derivative at 0 is 1. And the second derivative at 0 is 1. So what are we doing? We're matching the y value. We're matching the slope. And now we're matching the concavity. Pretty cool. Well, what second degree polynomial would make all these work? Well, of course, you see it right over here. It would be 1 plus x plus 1/2 x squared. So at 0, we get 1. The derivative is 1 plus x. So at 0, that's 1. And the second derivative is just 1. And so that works out as well. And you notice the kind of building pattern. So that second degree polynomial builds on that first degree, which built on the 0 degree. It's like we're always just adding another term. So let's go to part 4. And it's kind of, I wish I didn't just have to reveal the whole answer to you for each of these parts, that we could kind of discover it together in class, but that's the way it goes. Okay, for number 4, we need a third degree polynomial where the original function at 0 is 1. The first derivative is 1. The second derivative at 0 is 1. And the third derivative at 0 is 1. That's f triple prime there. It's hard to read. So we need all 4 of these things to be true. So what third degree polynomial would make that work? Well, it's going to be 1 plus x plus 1/2 x squared plus 1/6 x to the third. At 0, we get the 1. The first derivative would just, at 0, would be 1. The second derivative at 0 would be 1. And now the third derivative would simply equal 1. And so the third derivative at 0 is 1 also. And if you want to check these 4 things yourself, I welcome you to do that. But the point for us here is to notice, hey, once you're comfortable that this is the polynomial that makes that true, I should say, then we just notice, oh, we're just adding on another term each time. So it went from 1 plus x plus 1/2 x squared plus 1/6 x to the third. Number 5, I have on the next page, says take a guess at the fourth degree polynomial. Well, maybe I could have given you an opportunity to pause there and take a guess instead of just showing it to you, but here it is. So we got those first 4 terms, and we're going to add on another term. It's going to turn out to be 1 over 24 x to the fourth. Why is that? So then if we take 4 derivatives, times 4 times 3 times 2, right? The fourth derivative will work out to just be 1 when we're all when it's all said and done. And then the rest of them are still going to follow through with their derivative pattern as well. And so we will have the original function at 0, and then the first 4 derivatives at 0 will all equal 1. And to match all of the derivatives at 0 for our original function, e to the x. Now what's really impressive, if you graph this 4th degree polynomial and the previous one, that 3rd degree polynomial, in Desmos along with e to the x side by side, and I mean, it just blows me away what we're able to do here with what's relatively simple once you know just anything about first derivatives, or derivatives of polynomials, I should say. So we've come to number 5, the 4th degree polynomial that would continue that pattern. So number 6, could we take this to the nth degree? Maybe I'll pause here and let you guess. So what do you notice here happening? And maybe you realize, ooh, okay, so maybe these first 2 are kind of a little different, but then I see 1 over 2, 1 over 6, 1 over 24. Do those numbers 2, 6, 24 remind you of any kind of a known pattern? And maybe you know factorials, 2 factorial, 3 factorial, 4 factorial. Okay. Even if you go back to these, you can think of this as 1 over 1, and 1 in the denominator is 1 factorial. This is even like 1 over 0 factorial. Okay, so that's our pattern, right? We really see it here, 1 over 2 factorial, 1 over 3 factorial. The factorial will always match the degree. So we could say plus dot 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 1 over n factorial x to the n. And then we can look back and realize, oh, these even fit that same pattern. 1 over 0 factorial x to the 0. And 1 over 1 factorial x to the first. So this is it. The nth degree polynomial, and we can go as high up as we like, and the higher up, the higher n we are looking for, we can approximate f of x equals e to the x centered at 0 better and better and better and better and better. I'm going to show you the graphs here on this video in a moment to just kind of highlight what is the centering at 0 and what is that all about. Well, let's take a look at the bonus. What infinite degree polynomial would be f of x equals e to the x exactly, right? We recognize that these are approximations, but if we went infinitely far, we'd get it exactly. Well, could we write this as an infinite series? Sure could. There's our nth term, and we're adding these things up. So the bonus is this. Take your nth term from n equals 0 to infinity. That will be e to the x exactly. Isn't that incredible? E to the x can be written as this infinite series. So whatever x value you plug in, you can plug that x value in here. And you can, if you take infinitely many terms, that will be exactly the same number. That is really, really cool. Okay, last thing before we close this video, I'm just going to show you what I had on Desmos. So give me a second here. I'm going to minimize what I'm looking at and bring this up. So here's, make sure it's oriented correctly. Oh, it looks like it's upside down. There you go. And you can see the camera right there. I'll try and keep that there nicely so you can see it all. I've got it all ready to go and get that out of the way. Okay. So there's e to the x. Here's that first 0 degree polynomial, right? Y equals 1. Not very interesting, right? Just the horizontal line. Okay. But then we got a better approximation, 1 plus x. So hey, it went through the same y value there at 0, and it has the same slope as e to the x, but otherwise not very impressive. It's not a bad approximation when you're near 0 though, right? Even that straight line is a pretty good approximation if you're close to x equals 0. When you get very far away, they start to diverge. Ooh. Okay, so let's get rid of that and go to the second degree. And oh, now we match the concavity as well. So not only does it go through that point there at 0, but it's got the same slope and it has the same concavity. So this is really approximating e to the x well near 0. The further away from 0 you get, they start to diverge. Here was the third degree polynomial. We had to zoom out even. I mean, that's such a good approximation. It's like you can't even tell the difference until you get fairly far away, especially on the positive side. And here was that fourth degree polynomial. And I mean, I have to zoom way out before you even start to see it separate very much up here on the positive end. Near 0, it's incredibly accurate. Even though they only agree at the one point, it's a very, very good approximation. Here we can see them diverge out on the negative side fairly quickly. But on that positive side, really good. Okay, well, that is the end of part 1 here. So I'm going to go ahead and stop this video right there. See you in the next one.